we're Team Wavy Lays. I'm Evan.
I'm Jordan.
And I'm Matt. And here's our GUI.
We'll first load the normal image, which is the dogimage.png, and then we'll begin to start encrypting the different hidden images inside the cover photo. One thing to note is I'll first start by using method 7 to show that you have to use methods 1 and 4 before you can use method 7. This is the same for methods 8 and 9. I'll also attempt to encrypt an image using method 10 to show that you have to use methods 1, 4, and 7 before you can use method 10, as seen here. You can, however, still use the decryption methods in any order, as you will see. So I'll start by loading a new image and then just encrypting all of the methods really quickly. Okay, so we've encrypted all 10 hidden images using the 10 different methods that we used for this GUI. And so now we're going to save the newly encrypted image and replace the one that we already have in our folder. And then we'll load it out onto the GUI, which is right here. Now, as you can see, I'm going to use methods in any order I really want. And it's going to load out the hidden images that corresponded with what I wanted to encrypt beforehand in the above part of the GUI. And as you can see, all of the images turn out in binarized black and white, which is what we're looking for, which is cool. So I've decrypted most of the images using the different decryption methods, and I'm just going to save the decrypted image, and it's going to be saved into the folder, and that's how our GUI works. You can also clear all to reset your entire GUI and start again.
To load the original image, we use the internal MATLAB function UIGetFile. This function allows the user to select a file on their computer. The filter specification in the parentheses specify the type of file required. There are two outputs, the file name and the path to reach the file within the computer. If the user selects cancel, UIGetFile returns 0, so we made an error message notifying the user to select an image in this case. Full file builds a full file specification by splicing together the path and file name. Then we can use imread to read this file specification, which reads the image and turns it into a matrix. Here, we also establish an array called encryption_use, which will be used later in our program in order to identify which encryptions have been used. The axes function uses handles to specify the desired axes to use for imshow, which displays the image. When we were using our decryption methods, for some reason we noticed that specks of the black and white from the lettering of the cover image was interfering with our recovered images. So here, we made a for loop to reduce the blackness and whiteness an indistinguishable amount. Once we did this, there were no more blemishes from the lettering on the recovered image. To load the secret image, we use the exact same method as loading the original, except without modifying the black and white pixels. However, we do flatten and expand the image.
Okay, so our flatten function first allocates a 400 by 400 array of integers called flat image and sets it equal to the flatten function of the image that the user chooses. Flat image, which is the new 400 by 400 array, is equal to the built-in function in binarize of the image that the user chose and of a degree of 0.5 on the gray scale. The built-in function in binarize takes the image chosen by the user and replaces those values with ones and zeros. Our expand function takes the flattened image data that was recently flattened by our flatten function and allocates an n by n array of zeros for the flattened image chosen by the user and assigns it to expand image. We then use the for loop, which iterates from 1 to the number of values in the flattened image chosen, and say that if any value n in the flattened image is equal to 1, therefore a white pixel, then in the expanded image, the corresponding value is also equal to 1. We then proceed to say that the expanded image is made into a new RGB or image or an x by y by 3 array with black pixels as zeros and white pixels as 1.
Before we start any encryption method, we use the encryption used list in order to identify if an encryption method has been used. If the element index corresponding to the encryption method is 0, this method has not been used, and we change the value to 1 and carry out the encryption. This means that if any element is 1 in the encryption used list, the method has been used and an error message is returned. For the actual encryption method, we base it off of the example given to us in the prompt. Basically, for method 1, we compared a pixel in the red layer of our cover image with the corresponding pixel in our flattened secret image. If the pixel in the hidden image is black, corresponding to 0, and if the cover image pixel was even, then we subtract 1 in the cover image to make it odd valued. Also, if the pixel in the hidden image is white, corresponding to 1, and if the cover image pixel was odd, then we subtract 1 in the cover image to make it even valued. This essentially makes it so that the hidden image is embedded inside of the cover image without being able to be detected by the human eye. Method 2 is the same, but for the green layer, and method 3 is the same, but for the blue layer. Methods 4, 5, and 6 are for the red, green, and blue layers respectively, but this time it subtracts 3. Methods 7, 8, and 9 are for the red, green, and blue layers respectively, but this time it subtracts 5.
Okay, so our 10th method uses a relatively similar thought process in relation to our other 9. Although the one flaw is that we have to use methods 1, 4, and 7 before we're allowed to use method 10. Through some trial and error, we found that if the secret image's binary value did not equal 0 and was therefore odd or even, we could subtract 10 to make the value odd again. And so to execute this, we first did a nested for loop which iterated for the 400 by 400 array and said that if the hidden flattened image equaled a black pixel, it would execute the solution that we found. We did the same for the hidden flattened images data for white pixels as well, and said that if the binary value was odd, we could subtract 10 to make it even, and if the binary value was even, we would end the loop.
Just like in the encryption function, we use the encryption used list in the recovery process to determine if an encryption method was used. If it wasn't, we returned an error message. If it was, we carry out the recovery. For the actual methods of decryption, we did some backwards thinking and applied the same type of logic we used to encrypt the images in a switch case. We first allocated a 400 by 400 array of 1s, white pixels, and created a nested for loop from 1 to 400 to look at each element. Then, if the difference between the double precision normal and encrypted file data equaled any sum of the integers between 1, 3, and 5, and if the modulus of the encrypted data in the specified layer was greater than 0, the recovered image's white pixel would be changed to black. This is how we determined all of the numbers you see here. They are all just different combinations of subtracting 0, 1, 3, and 5. In the red layer, we also had to add 10 per integer to include the potential possibilities for method 10 as well. We chose to do 10 because it made the numbers the same, just 10 greater. There were also little differences we needed to take into account about whether the numbers would be odd or even after subtracting 0, 1, 3, or 5. So in some places, we add 1 in order to take the modulus of the even or odd valued number that is 1 higher to the number in question.
So our method 10 decryption basically allocates a 400 by 400 array of 1s, which in this case are white pixels, and then creates a nested for loop which iterates from 1 to 400 twice, and says that if the binary value is odd again, then the pixel will be black in the recovered image, therefore equal to 0. We'll end the for loop and then use our expand function to expand the recovered image.
The save function used in our GUI operate at the end of the encryption panel and the recovery panel. Similar to UI get file, we use UI put file, which creates the file name and the path to reach the file. Once again, full file splices the path and file name together, and then imwrite writes the image data, in this case encrypt file data, to the file specified, encrypt full file. Should the user decide to start over, we made a clear button. To do this, we use the internal MATLAB function clearvars and specified global variables. This clears all global variables from memory. Then we made a matrix of all ones, which corresponds to white, called whitebox. We then showed this matrix in each of the axes, so each axis in the GUI appears white and clears all images shown.